Hey guys, welcome to A level chemistry and physics. Today we will be covering AS level work, power, and energy. This is also a very important part of your syllabus and it will introduce to a few new concepts that you may or may not have seen before. So, yeah, let's get to it. So, first, let's come to work. What is the definition of work? So, in everyday language, we use work in a lot of different circumstances, right? From lifting weights to doing the simple thing like writing an essay, any layman would consider this as work, right? Because you're working. In physics, however, work has a very specific definition. Work done is specifically referred to as the product of the force applied on an object multiplied by the distance traveled by the object in the direction of the force applied. So that's the definition of work. We'll get to an example that will help you understand what this is. So as you can see with the definition, work is equal. So the formula for it is W is equal to F into S, where W is work done, F is force in newtons, and S is distance traveled. The unit of work is joules, and why the unit of work is equal to the unit of energy, which is also joules, we'll also cover that later on. So this is the definition of work. This is a simple example I was talking about. I've taken this from the book AS A-level checkpoint physics, Cambridge physics. Sorry, this is the book is okay. It's not particularly great, but I do take references from there sometimes to help with some diagrams, which I obviously cannot make myself in PowerPoint. So yeah, so this is the example. If there is a car that is stationary for some reason, it's not starting, and then there is a person behind it who's applying a force, and then the car starts moving a distance. Then we say that work is being done. So, for example, if the force applied is 300 newtons and the distance traveled by the car after those 300 newtons has been applied is 5 meters. So, the work done is 300 into 5, which is 1500 joules. Also, one more thing, we assume that there are no resistive forces or external forces that are reducing the distance traveled of the car. This is just by itself. No external forces are acting right now. So these are a few examples I put together of doing work and not doing work. So doing work is pushing a car and it starts moving, right? Because you need, for work to be done, you need a force applied and distance traveled. For the same reason, pushing against a stationary wall is not work done because although you are applying a force, the wall is not moving at all. So when you do W is equal to F into S, the force is there, but distance traveled is zero, and F into zero will give you zero. So pushing against a stationary wall is not work. Lifting weight upwards. So if there is a weight on the ground and you pull it towards you, you're applying a force, and again it moves upwards in a direction, which is in the direction of the force. Again, F into S will give you a value. However, holding a weight in one position, let's say above your shoulders for a period of time, although your muscles will begin to tire, you're technically not doing work according to physics because you're not applying your applied force is not resulting in movement. There is no distance traveled. A falling stone is again work being done because, as you know, something will fall towards the earth because of the gravitational force exerted on it by the earth, right? So, if the stone is falling in the air, the earth is exerting an attractive force on the falling stone, and because it is falling, it is traveling a certain distance. So, again, F into S, where F is the gravitational force, S is the distance fallen, will give you a value. The moon orbiting the earth, on the other hand, is not doing work. This is because we know that the moon is in circular motion around the earth, right? But although there is a constant force on it, there is no distance being traveled. In a circular motion, we know that there is no movement towards or away from the earth. It is always at a constant radius from the earth. Therefore, there is no work being done because there is no distance being traveled. Right, so now we talk about the unit joules, right? So this is understood that energy transferred and work done are always numerically equal. So you might ask, how is that possible? So for example, when you're pushing against the car, the work you do on the car gets converted to the kinetic energy of the car as soon as it starts moving, right? Because we know kinetic energy is the energy due to movement, half mv square. So as soon as you apply a force on it, the work you do on the object gets it gets transferred to the object and the object gains kinetic energy. That is why the unit of work is also joules, which is also the unit of energy. Right, so this is again very important to remember. So Newton's, meters, and joules, these are units which we have to talk about. So from the equation W is equal to F into S, we see that the Newton, which is the unit of force, the meter, which is the unit of distance, and the unit of work or energy, the joule, are related, right? 1 joule is equal to 1 Newton into 1 meter, or 1 joule is 1 Newton meter. So now we can also come to define 1 joule, because now we know that it is 1 Newton multiplied by 1 meter, right? So the definition is written there. A joule is defined as the amount of work done when a force of 1 Newton moves a distance of 1 meter in the direction of the force. And because work is also equal to energy, we can define the same joule in terms of energy as well. Again, amount of energy transferred when a force of 1 Newton moves a distance of 1 meter in the direction of the force. Do note that this is completely independent of mass. Right? There is no mass over here. So if there is a 1 Newton force being applied on an object of any mass and it moves 1 meter, 1 joule of work is being done on it. There is no mass in this equation. However, obviously, if it has a greater mass, 1 Newton will not move the object that far. If it has a very high mass. If it has a very low mass, then a 1 Newton force may just move it 1 meter. So there's obviously that variable. So work done and direction. So we talked about work done's definition being a force being applied on the object and the object moving a direction, moving in the direction of the force. Right? In the direction of the force. That's important. However, many times in the problems in the AS level syllabus, what we'll do is we'll encounter problems where a force is at an angle to the object. So if there is just a block of wood lying on a table, a force will not be horizontal or parallel to the table. It will be at an angle to the table. So, since the definition of work is always the force, the object moving in the direction of the force, we may just need to resolve the force so that we take out the direction in which the object is moving. And we'll see an example like that. Right, so again, let's take an object that's lying here and the force of F being applied to it at an angle of theta. Right, so the red line you see, you can take it to be the table, and the force origin being the existence of an object. So we can assume that there is an object over here which is on which a force of F newtons is being applied at an angle of theta. So when we have to determine the work done by the force, we have to find the direction of F. We have to find the component of F, I'm sorry, that is in the direction of the object being moved. So if the force is in this direction, but the object is only moving parallel to the table, we need to find the component of F that is also parallel to the table. And this, as we know by resolving vectors, that this is always F cos theta. So work done will be F cos theta into the distance traveled, which is S. Therefore, work done is Fs cos theta. Again, this is just resolving the force F in a direction where the object is moving. That is important. Right. Now we come to work done and gases. So pistons are very important. Pistons are often used as examples to derive formula of work done by gases, right? For example, syringe is a piston. So in the next few slides, we'll also use a piston to help determine work done. So this derivation is very important. So on the right hand side, you see a piston, which was first, it was over till here. However, there was a gas in this section, which when it exerted a force, the piston moved this distance till here. So this is the initial and this is the final. So we will then derive the work done by the gas using a series of different formulae. Okay, so the definition of pressure, as we know, is force upon area. Right? From our previous knowledge, pressure is force upon area. So if you want to make force the subject of this equation, force becomes pressure into area. Right? That can be seen in the second line. Work done, as you know, is force into displacement or force into distance moved in the direction of the force. Right? In force into displacement, we can replace force with pressure into area. So we put this over here. We get work is equal to pressure into area into distance because force is now replaced. But now you see a quantity over here that is area into distance. The volume of any object is the area of the cross section into its height, right? And this, in this case, the area into the distance traveled is the shaded figure is a shaded part in the figure. This is the volume of the gas that has this is the volume that the gas gains by moving the piston, right? This is the increase in volume of the gas because it is again base area into height. We call this increase in volume delta V. Delta, which is the symbol is a triangle. Delta indicates that there is a change in V, right? Because when the gas moved the piston outwards, the gas had an increase in volume. It had more volume available to itself. So A into S can be replaced with delta V. Therefore, work done becomes pressure into delta V. Right? So this is a derivation. You use a pressure equation and then use it to replace force in the work equation. Then simply you will get A into S is equal to delta V. Right? Also, there is a built-in assumption that the pressure P is not changing as the gas expands. Okay, this is only true if the gas is expanding as it's written against the pressure of the atmosphere, means that there is a constant atmospheric pressure acting on it, which changes only very slowly. So if there's a drastic change in the pressure inside or outside the piston, it will lead to a drastic change in pressure of the gas. So it has to be at a constant external pressure so that there is not a drastic increase in the pressure inside the piston. Now we come to another um, term known as efficiency. Right, so till now, a basic assumption was built into all our calculations that is, there were no energy losses in any of them. However, we obviously know that in real life, there are always energy losses and no machine is 100% efficient. Right? There is heat, sound, light, so on and so forth. Therefore, we need a measure of the extent to which the input energy is converted to output. Right? So if you're building an engine, for example, you're putting in some amount of energy into it for it to do work. Like let's say you're making a car engine, you're putting it energy in terms of fuel. You want to see what percentage of that fuel is being converted into torque or in the movement of the car. So this ratio came to be known as efficiency, right? Because and this is layman terms as well, right? The efficiency of the car, efficiency of even a person, so on and so forth. So formula. The formula for the efficiency is, as was hinted before, useful output energy upon total input energy into 100%. Do note that sometimes the 100% is not given, so it is just useful output energy upon total input energy. When you multiply it by 100, you give it as a percentage, otherwise, you give it as a decimal. Both are acceptable in the AS level syllabus, you can give it either ways. For reference purposes, so for example, the human body is only 30% efficient. The rest of all energy, that is 70%, gets wasted mostly by heat and sometimes by sound. So human bodies are a very inefficient machine. So that was all about efficiency. It was not too complicated. So power, and this is very important. Power and work go hand in hand. Okay, power also has many meanings in everyday life, just like work. right? We talk about power hierarchies, power of a president, so on and so forth. However, obviously in physics, it has a very specific definition. Power is defined as a rate of work done, or to paraphrase, work done per unit time. That is power. And as hinted by the definition, formula for it is work done upon time taken, where W is the work done in a time T, right? So again, power is the work done upon time T. So now we come to the unit of power, which is known as the watt. Okay, the symbol for it is W. So the unit is named after a famous scientist known as James Watt, who developed a steam engine in the late 18th century. So it becomes obvious now why the Watt will be named after James Watt, because the concept of power and work are very important while devising engines. You would want an engine to do maximum work per unit time and be most efficient. So when you're talking about engines, these concepts of efficiency, power, work, heat losses, energy losses, so on and so forth become very important. 1 watt is 1 joule per second. So we just talked about how work done has the unit joule. So this is work done per unit time. So this is joule per unit time, or 1 joule per second. We also use many other units known as kilowatts and megawatts, and these conversions are written on the slides. You can find these yourselves also. I just wrote it down because it's easier that way. But one of the most commonly used units in the papers also is kilowatts. Kilowatts usually comes a lot, and megawatts is also present sometimes. The watt in itself is a very small unit, not used in everyday life. Kilowatts and megawatts are used more often. Moving power. Okay, this is also very important. So let's say there is a moving object, right? Let's say there's an aircraft moving with a velocity v. Its engines that are working constantly to push it forward provide the force F needed to overcome the drag of the air, right? So the air is providing air resistance to the aircraft, and the engines are constantly providing a force F in order to counter it so that the plane keeps moving. If the air resistance will become greater than the engine force, then the plane will decelerate and stop, right? So the engine needs to move constantly to overcome the drag of the air. Let's say it's moving at a constant velocity. Okay, let's say at velocity v. And when we calculate the distance moved by this moving aircraft, so distance is speed into time. So s becomes equal to v into t, right? So and then we move towards the work. Work done is force into distance. We now and then it follows through that distance is velocity into time, right? So once we replace distance in the work equation, we get work is equal to force into velocity into time, right? Force into velocity into time. Then we have to calculate the power for this object. Power is just work upon time, right? So it becomes force into velocity into time divided by time. The time gets cancelled out, and power is just left with force into velocity. So power equals force into velocity. Do note that this is the power of an engine at that point in time. So if if a moving vehicle is accelerating, let's say it was first at 15 meters per second and then at 20 meters per second, power calculations have to be at that instance at time, because that is the moment that that engine is applying an exact amount of force. That force can increase or decrease depending on the maximum value exerted by the engine, right? So power is equal to force into velocity is instantaneous. It is at that point in time. Sometimes in a lot of the papers, I've seen the derivation of power is equal to force into velocity. So it is better if you memorize this logically step by step, that we do this first, then work done, then distance, so on and so forth. But in many other questions, you can just directly use power is equal to force into velocity. Also, if you forget this formula, there are many questions you will not be able to solve, because in those questions there is no way of calculating work done and then dividing it by time. You would directly need to use force into velocity in order to get work done. I personally faced a lot of problem because I did not remember this formula, but only with practice it came to it, I found out how important it was. So please remember this formula as it comes very often. So that's it, guys. Thank you so much for watching. If you have any feedback or any requests, please leave them in the comments below. I do plan on increasing my upload speed. Intend to do one video every day. I'm working on the other one already. So I would first finish the AS level syllabus and then the A level syllabus. So stay tuned. Thank you for watching, guys. Bye bye.